Our current unit of study is going to be electrochemistry. Now, one of the things we're going to work with electrochemistry is the mnemonic device known as Leo the Lion Goes GER. This can help us remember the difference and distinction between the oxidation and reduction processes. What Leo stands for, the LEO, is that if we lose electrons, this identifies the process as being oxidation. Whereas if we go through the process and something gains electrons, the gaining of electrons is known as reduction. These two processes go hand in hand in electrochemistry, and that if something is losing electrons, somehow, some way, somewhere, something else has to be gaining electrons. An example of each process can be seen with what we have here. In the first, we have magnesium solid turning into magnesium 2+ ions. In this process, we can see the magnesium solid is actually losing 2 electrons in order to turn into a 2+ ion. This would represent a half reaction known as an oxidation half reaction is what's taking place here. Now the other half reaction, we can see that we have copper 2+ ions turning back into copper elemental copper solid. The copper 2+ ions pick up or gain 2 electrons to turn back into elemental copper, and this half reaction would be something we identified as being the process of reduction, when we see something gaining electrons as we move from the reactant to the product side. Now, one thing we've seen on the back side of our AP Chemistry periodic tables is there's a series of half reactions. Now, if one notices on this chart, all the half reactions written are specifically reduction half reactions, and each one has with it an accompanying voltage. This voltage accompanying each half reaction is something known as the reduction potential, in that it's only for the reduction half reaction. Another item of note on this chart is if we look right here, we see we have one half reaction with a value of 0 for its potential. This is specifically for the half reaction for the reduction of hydrogen ions into elemental hydrogen gas. This has a reduction potential of 0. Half reactions that appear above the 0 point on the reduction half reaction chart indicates that these particular half reactions are reactions that are more easily reduced than H+. So anything here that's positive, for example, we have the tin 4+ has a positive 0.15, copper 2+ positive 0.34. This indicates that these half reactions, the reduction process, takes place more readily than it does for hydrogen ions. Now, as we get more and more positive with these, that also indicates that a half reaction is getting more and more easily reduced when we see a more positive or a larger value for our half reaction reduction potential. Now, on the bottom side, below hydrogen, we see half reaction reduction potentials that are negative. When we have a negative half reaction reduction potential, this indicates that for these particular half reactions, they're more difficult to reduce than what we see for the H+ half reaction, which has a value of 0. Now, in electrochemistry, what we're often called upon to do is combine two half reactions to make a whole reaction. Now, when we combine our half reaction, we have to make sure that one half reaction is a Leo, or represents the process of oxidation, and the other half reaction has to be a GER. These go hand in hand. The reduction process is always accompanied by the oxidation process, in that if something is gaining electrons, something else has to be losing electrons, which would be the process of oxidation. Let's do an example. Here we have two half reactions. One is for silver ions, and the other one is for aluminum ions. If we look at our reduction half reaction table, we can find that the reduction half reaction potentials for each is listed. The half reaction potential for our silver reduction half reaction is a positive 0.80 volts. The half reaction reduction potential for the aluminum reduction half reaction is a negative 1.66 volts. What this tells us is because the silver has a value that's more positive than what we see for the aluminum, is that the silver half reaction is more easily reduced than the aluminum half reaction. Consequently, the aluminum half reaction would be more easily oxidized. So the aluminum half reaction, we're going to end up flipping it and switching it from a GER and turn it into a Leo half reaction, so that when we combine these two, one half reaction will represent reduction and one half reaction will represent oxidation. Now that we've taken the aluminum half reaction and flipped it, that's turned this half reaction into the process of oxidation. We now have a half reaction, one of which is reduction and one of which is oxidation. These two half reactions can now be combined to make a whole or an entire electrochemical chemical reaction. Now, one item of note over here is that the potential for the aluminum half reaction, by flipping the reaction and changing it from a reduction to an oxidation half reaction, the sign on the voltage here has changed from a negative to a positive by virtue of writing the reaction in the reverse direction and making it an oxidation. Before we add the two half reactions together, we have to make sure that the number of electrons being lost and the number of electrons being gained is the same. So the first reduction half reaction, we have to multiply the entire reaction by 3. This now gives us 3 electrons being gained, which is the same as our 3 electrons that are being lost. The two half reactions can now be combined to make a whole reaction. When we combine the reactions, the electrons are going to cancel, leaving us with this as our overall balanced electrochemical reaction. Now we also need to add together the half reaction potentials to give us what's known as our E cell value. Now the calculation right now is for standard conditions, so the voltage that we would get right now would be representative of when we have 1 molar concentrations for our aqueous solutions. Adding together the two half reaction potentials gives us an overall reaction potential for the cell, the electrochemical cell, of a positive 2.46 volts. This would indicate that for this reaction, this reaction is spontaneous, and not only does the reaction occur, but the reaction will produce 2.46 volts, which can be written over here on the product side, indicating these chemicals will react, we produce our products, and 2.46 volts is also something that comes out as a result of this electrochemical reaction. If, on the other hand, when calculating our E cell value, if we were to get a value that is negative, that would indicate that the reaction, as written, would be non-spontaneous if we get a negative value for our E cell. In fact, that would indicate in order to make the reaction happen, we'd have to add the voltage to the reaction on the reactant side to push or force the reaction to occur. Another item in our electrochemical reaction is being able to identify what's being oxidized, what's being reduced, and also labeling what's known as the oxidizing agent and also the reducing agent in the reaction. In this electrochemical reaction, the silver aqueous ions are being reduced, and that they have to gain electrons to go from a positive aqueous ion to turn to elemental silver. So the silver 1 plus ions aqueous is what's being reduced. Now, by virtue of being reduced, the aqueous silver ions are also known as the oxidizing agent, and that by virtue of being reduced, the silver 1 plus ions cause the other chemical in the reaction to be oxidized, so the silver ions are also known as the oxidizing agent in this reaction. Meanwhile, what's being oxidized is the elemental aluminum, and that the aluminum, since it starts out in its elemental form, it has to lose electrons to turn into a positive 3 ion. So the aluminum is being oxidized in this particular reaction. Now, by virtue of being oxidized, the elemental aluminum is also known as the reducing agent in this reaction, in that by virtue of being oxidized, the aluminum is causing the other chemical to be reduced. When the aluminum loses some electrons and gets oxidized, it's losing its electrons to the other chemical, which gains them and gets reduced. Therefore, the aluminum, elemental aluminum here, is also known as the reducing agent in this particular electrochemical reaction.